So in this video I am going to cover how we implement a custom peripheral for the AXI4-Full interface. And the example I am going to select is the Pixel processor, the one that you know already. So what I am doing here is just following along the instructions on this tutorial in number 4. Okay. So the design looks like this, right? Remember the two FIFOs, the circuit itself, the state machine, the blue one that controls, let's say, the outer side of the FIFOs, and also the this red state machine that controls the inner side of the FIFOs. Okay. So you need to, of course, download the files that you have available, and if you download them you will have these files. It's a bunch of different files. Okay, I think I can explain this in a better way right here. Here. Before we start, let me just mention the following so you don't forget. What is the design flow when you have to design, a custom peripheral? Well, the first thing you have to design, of course, is the circuit itself, right? Whatever circuit you want to work on, whatever you want. And as always, it is important to simulate it comprehensively. After that, the second part is you add the interface circuitry so that you create the peripheral, right? The peripheral, remember, is just what? It is your circuit plus the AXI interface. Okay, and of course you have to simulate the AXI interface. I think this step is extremely important. And the recommendation is always to create its own Vivado project for the peripheral. Okay. Once you complete these steps, these first 1 and 2, believe me, the next 3 and 4 are just mechanical steps. It's just click here, click there, do this, do that. They become very repetitive. The most important ones are actually 1 and 2. 3 is just you build, quote unquote, your peripheral in Vivado, so now it is just ready to drag and drop it into any embedded system. And then number 4, you integrate everything in the embedded system, right? And then you test using the drivers that are provided. Okay. So the first example, like I was saying, is the Pixel processor. And the Pixel processor has a particular structure, of course. Here. Right here. Let's take a look. Has this file, my Pixel V10. That is the top file of the AXI interface. Now remember, this is a template, right, provided by Vivado. Then there is this file. That is the file that implements most of the AXI interface, by the way, most of it. This is also a template provided by Vivado, and this part is important because we are using a different approach with some significant modifications by me. Okay. Essentially, what I did is as I said to you in the previous lecture, I included these two FIFOs and I modified the generation of this particular signal. Now, this signal is also controlled by the this empty flag of the output FIFO. That is the main difference. Okay. To do that, I had to create a bunch of other files. So we have this, my AXI IP It's just a wrapper file. It's actually not doing anything. I created mostly for the purposes of the pixel processor, and you can use between using the FIFO-based approach or the memory-based approach for the pixel processor. To be fair, we're going to focus on this one only, okay? And in any other examples, you will see that there is only the FIFO-based option available, okay? And then we have this file, the one that actually implements the FIFOs, okay? So this file here, of course, has the FIFOs. It also includes the blue state machine, the one right here, and it includes, in this case, the red state machine. Let me say something here. This is unique. This is only for the pixel processor. So only for the pixel processor we are including the red state machine in this file. You will see in the other examples I don't do that. The reasons are mainly legacy reasons. Okay. So that's what you do in this file. And of course, obviously, you have to also do the following. The instantiation of this file. The one underneath it, of course, is the one right here. What is it? It is the circuit that you need to build. What is that? Let me explain. I think, by the way, I already explained this, by the way, but let me explain again. Ideally, it should contain the FSM at clock effects, and I think that's what you should be doing in any design. But again, mainly because of legacy issues, I somehow ended up including the FSM at clock effects in the previous file. But anyway, ideally that's what you should do. And also in this file, you have to do implement the glue logic. Let's call it like that. The glue logic between your circuit, right, and the FIFOs. What is the glue logic here? Well, it is the connection between the FIFOs and my circuit, which is actually these two lines. And as you can see in this case, the glue logic is actually very, very simple. It's actually trivial, right? It's just a simple connection. Okay, that's why, you know, this glue logic for this example is actually trivial. Okay, and something else that you do, or you should do here in this file, on top of it, you set up the parameters of, not set up, I guess, assign the parameters of your circuit. Okay? And after that, you have the circuit here. Sorry, underneath that you have this circuit, right? This is the top file of your circuit, right? Okay, so let me just quickly show you what this is. So for example, you can always download this file, and you can find, for example, lootgroup.vhd. If you were to open it, you see is what? That is your circuit. How it looks, which inputs it has, it doesn't really matter, because you designed this circuit the way you wanted it. Okay, that's all. What really matters is that file on top of it, the one that you have to build. The wrapper, right? So, and let's do that then. So that would be, let's see, right here. Again, the names, I mean, are kind of a bit weird, right? I think I should have selected here, I don't know, maybe pixprocessor.vhd, and here I should have selected pixprocessor_ip.vhd. I think that's what I should have done, but again, for legacy reasons, I ended up using slightly different names, of course. So let's take a look, a quick look at this. So this circuit here only has input what? The data coming from the FIFO, and as output that is the data that will go to the output file, of course. The parameters, as I said to you, this is the top file of your design, and you set up the parameters here. Whatever parameters you have, you set them up right here on this file. Okay? What else? And of course the glue logic. Remember this connection between this time, the output of this FIFO and the input of my circuit. So that is done actually by this simple for map statement, right? At this moment, that's where you are setting up the glue logic. But you know, but as you can see, it is very trivial, right? It is very, very trivial. In any case, having said that, so that's all we have. And the AXI4, well, if you want to see, for the most part, you won't need to, you know, mess with this file at all. All it does is actually, of course, you have the instantiation of your static IP, and here you have the, let me see, we modified a little bit the generation of the AXI-R valid, and we also here, look, clock effects. This is the state machine of the red state machine, and the one right here is the state machine of the blue state machine, right? The whole thing right here, sorry. That is the blue state machine. Okay. So like I said, usually you won't need to modify this file at all. And of course the FIFOs are here. These are the FIFOs, believe it or not. Those are all the FIFOs. Okay. In any case, for the most part, your job will actually be building this kind of file, the one on top of your circuit itself. Okay. So having said that, let's get started now with this. Like I said, oh, sorry, just one last thing. Sorry. Again, like I said, you need to simulate the AXI interface. And because of that, in this example, I am providing you with a test bench. Okay. The good news about this test bench is that if you want to reuse it for your own circuit, you don't need to modify much. You might need to modify, for example, the name here, here, and here. That's okay. You might also need to modify the name of this component, right? That's all, because the IOs are the same, because those are the IOs of the AXI interface anyway. And nothing else. You might need to modify, let me see, here, no, here we begin. Again, the name of this component, this thing stays the same, okay? One important thing about this test bench is that I already have here included some specific procedures to write data on the AXI bus, and also to read data from the AXI bus. And you know, so you are avoiding having to write all this you know, code right here. So how does it work? Easy, right? Look at this. We specify the data to writing, we specify the size, and then the memory address where we want to write. Okay, and all of these signals are the same, by the way. You don't change them. So that's how you write one 32-bit word. And then here you read a 32-bit word. So you write and read. That's all that you do. So when you have to test out your circuit, all you have to do is maybe you need to write different data, or maybe you need to write more than one word. We will see that later how to do that, okay? But I believe this is actually much simpler to edit for you, so you can simulate this properly, okay? Okay, so what else? So now we can start. So let's just get started. And of course, like I said, in all of these designs, to make it simpler, we are just tying or connecting the clock effects to this clock, the blue one. I mean, ideally, this clock effects should come from a different source, right? But to make it easy in this example, let's just, you know, hook them up together. So let's create a new project in Vivado, my AXI-Full Pix. So I already have here my folder, and I am going to, let me see, new, my AXI-Full Pix. Like I said, what I'm going to do right now is actually very repetitive, very mechanical. You will do this over and over, okay? And now, what do? You open a new project, you create a new project, sorry. It's going to be my AXI full piece, right? And I don't add any files, just make sure that the target language is VHDL, of course. Don't add anything. And then on boards, of course, you need to select the AXI, the ZYBO. The ZYBO or the ZYBO Z10. I'm using the ZYBO Z10 in this example. So here I go, and then I finish. Okay. Remember, we already have done this part. I have created my circuit already, right? This is the pixel processor that I developed a long time ago, and then I have already added the interface circuitry to it to create the peripheral. Okay, that is your job. Okay, and I mean, I hope that in the notes of Unit 5 it is clear how you can do that. Your job again is to design this file right here. Okay, but everything else is just kind of the same. Okay, once you do that, you simulate. I have already simulated that. If I have time later, I will probably show you the simulation, probably. And now we're on 3 and 4, which are the the simple steps. So what do we do here? We have to, according to this, we have to build our peripheral in Vivado. So we have to create the peripheral. I mean, like I said, our peripheral has already been created. I mean, even though it is shown here in a zip file, right? All of this has been I created a Vivado project and I simulated it with this test bench already. I have done it already before. So now we're just making it formal in Vivado. So Vivado knows, to drag and drop it. So what do we do? Oh, tools, create and package a new IP, new peripheral. And then the name is very important, because if you already have a particular name here, right, you have to use the same name, so you can just, copy and paste these files right away. My pixel, right? So let's remember that. So again, this file, the whole thing, the whole design is called my pixel. Okay. I think I mentioned this before. Sorry. I'm trying to give you everything so it is more clear. Just a moment. Here we go. So the structure would be like this. Let me just zoom in a little bit so it's a bit more clear. So the structure is like this. You have the top file, which will be my pixel, of course. You have the file right underneath it, which will be my pixel full version 10s00 AXI. AXI4, and here, instead of my COM2 IP, I have static IP. And instead of this, I have, for some reason, I ended up calling it loot group. Again, it's a weird name, but that's the one that I selected. But the whole thing is called my AXI pixel. Okay, so keep that in mind. What is my static IP again? In case you have forgotten, well, it's just this portion here. We include here the state machine, There you go. Okay, so that is that portion is the static underscore IP dot views. Okay, my AXI4 is the one that includes these FIFOs, right? And this state machine, and then everything on top of it is just the extra circuitry we need to interface with the AXI signals. Okay, so now I hope that makes it hopefully a little bit more clear. Here though, you have to select, of course, now instead of light you select full interface. Okay, by default it will create a template with 64 bytes of memory or 16 32-bit words. Okay, you keep it like that, and then you select edit IP. Okay, and now that you do that, your job is just to copy and paste, in particular parts. So we're gonna grab the entire group of files, except of course for the test bench, right? We don't need a test bench, because that is not a design file. And what we're gonna do, we're gonna just copy those files in a particular folder. So when you do that in Vivado, a new project will open, and this project, of course, it's taken a little while, by the way. Let's give it a moment. Will provide you with the templates, right? But remember, the templates are only the templates. I mean, it only includes the memory, and we don't want the memory. It has here all the signals that we need, by the way. Looks very similar to the one we have, but it also, let me show you in a moment. Yeah, it also includes this template for a memory. This whole thing is implementing a memory, by the way, believe it or not. So this is not what we want, so we're going to remove this, okay? But I mean, the edition of this file is a bit more complex. So instead of trying to edit it, I just use what I had before. I'm going to just copy and paste. So I'm going to copy these files right here into the IP, right, that I am creating. Is IP repo, my PSoC, HDL. You see these two templates. I'm gonna just paste not just those two, but also the other 10 files that I have, including the text file, because for some reason this particular project requires a text file. I'm gonna replace, of course. Once I replace, that's not enough. This will be replaced, of course. I need to, let me show you quickly to show you that it actually has replaced the files. Let's give it a little bit of time. Here we go. So it's the same file, but we made some changes. We commented out the memory, and we included our block, where we say, you know what, I want this to use a FIFO approach. But you can also use the memory approach or the pixel plus memory approach. These are, by the way, legacy options. I mean, right now I think we will start only with the FIFO approach. And in the further examples that I have, you will see that only the FIFO approach is available. Okay? So now, of course, this file requires all the files underneath it. I'm going to add them to my design. I go to add files. You have to be careful here. Select the proper file, my PSoC, right? HDL. Of course, these two I don't need to add because they are already there. By default, I mean, this was not a problem in Vivado, the previous versions, but in this version, 2019.1, for some reason, this option is checked. And that only means the following. I think you already know, some of you already know. That means that if I check that version, all these files except for the text file, because you have to add that manually, will be copied into a new folder here called src. I mean, that's fine. I mean, that is kind of repetitive, but we are not going to do that, to make it simple for us. Either way is fine, by the way. And now we finish. Okay. So now, what else do we do? We're going to run the synthesis, by the way. If at some point it complains that you need to, it cannot find the text file, by the way. If it complains that it cannot find the text file, make sure that the text file, of course, is located in the same directory as this file, because this is the file that calls for the text file. Like in the previous case, if you had checked that option, it would have created a source file, a source folder, and it would have copied only the VHD file. So you would have had to add manually this file to the source directory. That's why I didn't check that option, not to make this process even messier than it is. In any case, even if you are fully confident that this has been tested over and over, it is not a bad idea to synthesize, just to make sure there are no weird mistakes, like you forgot to include one file, for example. That's pretty common. Okay. So again, let me remind you that we are just following this tutorial, right? We are just following this tutorial. Let's give it a little time, okay? Okay, so now it completed. So now, of course, we don't run implementation. We just cancel this part. We go to the project summary. We check if there are any warnings. I'm sure there will be a lot, but you're supposed to have checked for warnings in the previous when you created the Vivado project for only the interface. Okay, and so what's the next step? Just to package our IP. That's the way it is called. So we go here, because why is this thing unchecked? Because we added new files. So we do merge changes with a little bit. Let's go back here, and then we're done. Click on repackage IP and click on close the project. So now our IP, which is the pixel processor peripheral, right here, this block is ready to use. It's ready to use. You can just stop right there. You come another time and you can add that block later if you want. But we're gonna do it right now. So here we of course open the canvas here. It's taking longer than expected because I am recording. Let's give it a little while. In any case, this software, it's heavy, by the way. Okay, if you are using a laptop, never try to run this software while your battery is not plugged, because by default, I think it will turn into the battery mode, and it will take longer to run Vivado. So we add, of course, the PS. That is the microprocessor system, and then we're going to add our block, my AXI4-Full Peripheral. Yeah. You look for it, and my pixel. So, there you go. Now all you have to do is to just here run block automation. And then run connection automation. Split a little bit of time. Now let me talk to you what do I mean by this, because this will become important when we have to deal with partial reconfiguration later. Look, in the ZYBO Z7, for example, the clock input for the PL is 125 MHz. That is the crystal. But by default, the PS only provides a 50 MHz clock to the PL. But in the ZYBO, by default, it is 100 MHz that is provided. This clock, of course, can be changed by you. How do you do it? Well, you just go onto the PS, right? You double click on it, and you will see that there are a bunch of different options. For example, clock configuration, PL fabric clock. Look, by default it's 50. You can always change this number to 100, for example, right? And it is 50 because I am using the ZYBO Z7. If you are using the ZYBO, it will be 100. But that you can change on your own. Okay. So now, what do we do then? Well, just in case we validate the design, we are not adding any IOs to our peripheral, right? Like in the one for a previous example, remember? So this process should be easy. But remember, it might be possible, maybe you want to do this for your final project. It might be that you want your peripheral, right, to be tied to LEDs as well. Well, in that case, just use the steps, laid out in the tutorial number 2, I think. I also posted a link, I think, to the tutorial of the Zinc book. They also tell you how to do that. Okay, remember, you have to edit the XZ file. It was a bit messy, it was not fun, but it is entirely doable, by the way. So now what next? We go to sources, and we're going to generate a HDL file, a VHDL file that will be the wrapper, which is like a VHDL file representing the entire architecture. Okay, everything, the entire embedded system. Okay. And after that, we need to synthesize, and then implement, and then generate the bitstream. Remember that there was a problem, right, with the text file. That's kind of a very annoying problem. I mean, I started doing this a long time ago, and even up to now, they have not fixed this issue. I have not found a way to fix this issue in a better way. I had to do it manually. Now you might be wondering, why do I have a text file? Well, because I'm using an LUT based project, so I read data from the LUT to implement my circuit. Okay, you will find that in many cases you might need to do that. You might need to read from an LUT text file. But in other examples like the divider or the convolution kernel, you see that you don't need to read a text file. Or even the codec, right? You don't need to read a text file. That makes your job much easier. But it is not uncommon to read a text file in your VHDL design, by the way. It's actually pretty common. Okay, so now that we have that, what do we do? Well, we run synthesis. And when you run synthesis, what's going to happen is that in the project, right here, in the sources, right, it will generate a bunch of different files. And well, it will, of course, it will copy the VHD files of your circuit, right, somewhere here. But the problem is we don't know where that somewhere is. And the main issue is that it will only copy VHDL files. It won't copy text files. And then, of course, when it tries to synthesize, it will fail, of course, the first time. So it's actually here, I know, I guess just because of experience. And it will create a bunch of folders this way, with very weird names. I mean, you can, if you want, you can try to check and figure out where it is, right? But there is no reason for you to do that. I mean, it's better to let the error in synthesis tell you where the file needs to be at. Okay, so what we're gonna do is, of course, just copy this file, and we're gonna wait until Vivado tell us where the mistake is to place the file manually. Okay, just give it a little bit of time. This takes a while. Okay, and as you can see, it failed, right? As we knew already. So what do? I think there are many ways. One way is to go to the messages, and you just scroll down all the way to the error, and you will see here it says unable to open the text file, of course. Which file? This file is the one that is unable to open. But look at this entire, path. You have to copy your text file right here in this path. So what I'm going to do, of course, is grab this text file and then go to that specific location. So according to that should be 160 right here. HDL. Like I said, this part is not very fun. And there you go. And once you do that, now you are ready to start over. And you can just, I will feel confident, we can just go all the way to generate bitstream. Okay, and you let it run this. It will take a while as well. Okay, so now it completed the generation of the bitstream, and well, we have to just now export the hardware to the software project, and now we launch SDK. Now remember, this step right here of exporting the hardware, you should only do it once, and then from here you can launch your SDK. Okay? So now let me tell you what's going to happen. If this is the name of your design, right? SDK will create software drivers, and they will be actually in the following file, mypixfull.h. And the software drivers, I think they have a particular name. I think it's M write memory. I think that's one. And the other one is my pixfull M read memory. Okay, and they have particular input and output. Okay, I will show you in a moment. So those are the, I think there is one more, but those are the two most important ones that you can use. Because how do you communicate with this peripheral? You have to write on a particular position in memory and read from a particular position in memory. In this particular FIFO configuration, there is no need for you to specify a memory position. Meaning any of the 1632 words where you plan to write will work as well. That's why we have 6 bits here for the memory. So you don't need to do anything. Any of the 16 memory positions will work as well. You can write on any position or address and it will work the same. Okay, we will see later that it is possible to decode particular memory positions such that you do specific instructions, but that's later, not for now. Okay, so now we go to SDK and we follow the tutorial, right? We open a new software project called Pix Test. Go to new, and then I'm going to create an empty application, and then I complete. And when that process completes, you will see that you will create the drivers. Okay. It's going to take a little while for that to complete. I think it's taking longer than usual, but once it completes, it will create the drivers for you. It should be there already here. So we go to the PIC. That's the PICs test. That is the empty file, of course. But the BSP, which is the the board support package, that is when actually, if you open it, you will see here the entire library, all of the peripherals. Most of them, by the way, are peripherals of the PS. The only one that I think it is for the PLC one, my PICs full. And you go to source here, and you will see in source this file .h. That is the one that has my function here. So all you do is write memory, write and read memory. Those are the only two you need. Okay, and as you can see, for write memory, you provide the base address, of course, of your peripheral in the microprocessor's memory space, plus an offset, of course, because what is the offset? Well, that is this address, these 6 bits. Remember, we only use the 4 MSBs, right? And again, like I said, in this particular example, since we're using FIFOs, we can write on any of the 16 addresses and we will be fine. So in that case, the offset in this particular example of the pixel processor can be anything, okay, from 0 to 15. And then we include the 32-bit data. And the same for the read memory. We only specify the base address plus an offset, okay? And we read data. Of course, you have to specify here a value, right? This is a return value for the read memory, okay? That's how you do the writes. Now, these instructions can only write data one 32-bit word at a time. Okay, let me just tell you. Here, of course, there are no bursts. Okay, we only write one 32-bit word at a time, or read one 32-bit word at a time. So now, what we have to do, of course, is in our project here, we have to add our file. And again, I'm gonna just copy what I have because I already have a pre-written file. I'm gonna copy it right here, SDK, PICs test as the name of your project, and then source, and then copy. I am sure there are better ways to do it, by the way, but okay. So now we go here. We have to refresh at F5, right, to load that file and let it compile. By default, it will compile automatically. In any case, I was just saying that these are the two main write and read functions, right, for the software drivers. The question is now how to do bursts, right? Because that is the whole point, right, of using the AXI4-Full interface. The idea that we can write much faster. If we are only writing and reading one word at a time, I guess there is no difference with the AXI Lite interface, right? That is correct. So the way you do bursts, we are not going to cover it today, but just to let you know, we will have to use something called direct memory access, DMA. Okay, this uses the DMA controller in the PS, right? It has specific functions, okay? But we will do that later, not now. But this is just to let you know what's coming. Okay. So for some reason, this thing takes a lot of time in my Windows 10 computer. It doesn't take a lot of time in the Windows 8. Okay. But anyway, let's let it finish, and then we will continue. Okay, so after a little while, of course, it compiled, and then we can open this file right here, and you will see, what it's doing. Like I said, everything is right here, right? So you can use, I guess, this file as a template, right? And instead of my pics full, it will be, you know, my example .h, right? Something like that for your particular case. Instead of this base address, because the base address is apparently a parameter, it will be like something like this. This is in case you wanna, you know, use it. You wanna edit this file. It will be something like this. So let's say I call it my example. So that will be then something like that, my example. For example, what else? Well, instead of this, right, it will be like this: my example underscore m right name. And the same for read. Okay, so you will see it will be very similar. Everything will be very similar. So what happens here? We are going to write 4 words on the base address and then read 4 words. And notice when we read, we're reading from the base address plus an offset. Again, this doesn't really matter because, as I explained before, this is a FIFO system that in which the address doesn't matter. It reads anyway or writes. Okay, so now we have to double check, right? And here is the test case, and we're supposed to get this. If you get this, that means that you did the right thing. So what do we do first? We have to connect the board. We program the FPGA first. Takes a little while. Once you program, the serial port will be available. You go to the terminal, you add the serial port. It should be here. I think it's COM10 in this case. And then you click OK, and now you are ready to run the software routine for the software application. You go here, fix test, and then run as okay. Let's see if this works. Well, oh no, this is a moment, sorry. Before we do anything, remember, I think by default, I always try to uncheck this, because every time I make a small change, even if it's comments, it's gonna want to compile everything again. So I don't want that, because sometimes compiling might take a while. Let me see again. There you go. And here is the answer. As you can see here, this is what we get, right? And we compare to what we have here. 0F8, 87, so yeah, it's okay. Okay, so that's a simple test. As you can see, this is as you have seen, these steps are pretty straightforward, right? And feel free to use this as a template, right, for your files. All you need to change is the name of the peripheral, right? The name you selected. Okay, we change it in here, and in here as well. Okay, all right. Again, these are just mask functions. Actually, the real function, as you might have guessed already from my previous example, to write and read is the cell, I think it's out 32 to write, I think, and cell in 32 to read. If you go to the pixel here library, this is what we have, you see? So if you, by the way, use this particular function, this will work for every example you have. You don't have to change the name, okay? And the same for reading. Okay. All right. Well, thank you so much. Okay, and I will post another video soon for another example. Thank you.